Let's start with an idea that surfaces exert forces. It's not a new idea. It's a hypothesis, a successful hypothesis that explains many of the things that liquids do. I can demonstrate these forces by catching a soap film on a wire frame. The fact that the tension in the film is uniform in all directions explains the circular arc of the thread. To enlarge the film, I must do work. Force times distance. Pulling down the thread increases the area, takes energy to pull more molecules up into the surface. Another example of the pull of surfaces is given by a loop of thread placed on water. Soap molecules lower the surface tension of water. The higher pull of the outer surface pulls the loop into a circle. The old camphor boats operate on the same principle. Where the camphor touches the water, the surface tension is reduced, and the higher surface tension on the bow pulls the boat forward. Particles of camphor scraped onto a water surface will also move. The camphor dissolves unevenly around the edges. In this film, we shall examine the effects of these surface forces on the shapes and the motions of liquids. The angles at which surfaces intersect are determined by the pull of surfaces. If three soap films meet, they must meet symmetrically in order for the pull of the surfaces to balance. The angles are all equal, all of 120 degrees. More than three films cannot intersect, except momentarily. You can see that four films meeting are unstable. A more complicated circumstance occurs where solids and liquids meet. With drops of water on wax, the water, the wax, and the air clearly do not occupy the same angles. It is not so readily apparent that solid surfaces exert a pull. Instead, it is more useful here to consider surface energies. Just as it took work to pull out a liquid surface, it takes work to create a solid surface. The contact angle is that which leads to the minimum available energy of the system. Here is mercury on glass. Notice that the mercury angle is larger than 90 degrees. If the liquid angle is larger than 90 degrees, we say that the liquid does not wet the solid. With a drop of water on a bar of soap, you see that the liquid angle is less than 90 degrees. The water wets the soap. If we accept this hypothesis that surfaces exert forces, we find that there are three boundary conditions expressing these forces that need to be used with the continuum equations of fluid mechanics. We've just seen examples of the first, that where surfaces meet, the contact angle is uniquely determined by the energies of the interfaces. The second boundary condition comes from a force balance across surfaces. One finds that a curved liquid surface has a higher pressure on the concave side. For example, the higher pressure inside forces the smoke out.